This is going to be a demo of the comparison of speed and accuracy between ParaDEVS and traditional Monte Carlo simulations using DEVS streaming framework for parallel and distributed simulation. So the two frameworks involved here is Paratemporal DEVS or ParaDEVS, that being a modeling and simulation technique to increase the speed and knowledge of data acquisition for stochastic systems. So this leads to faster and increased knowledge of the system under simulation compared to traditional Monte Carlo sampling techniques. And then Dev Streaming Framework is a framework that's being leveraged here to simulate DEVS models in parallel. And this works by communicating between a root coordinator and dev simulators over Kafka message topics. The SES, this is the top level description of the model. A better view of that is in MS for me, the Eclipse version is shown here. So there's a tree showing the system entity structure, and essentially there's two strategies involved for the missile defense system. So there's the shoot, look, shoot strategy and the single shot strategy. These are two sort of well-known missile defense strategies. And the sequence of messages that flow through the system, essentially the system gets a detection, the battle manager sends out a launch sequence to the interceptor, and the interceptor will report either a miss or hit back to the battle manager. Depending on the strategy chosen, this cycle might repeat for shoot, look, shoot, for example, but once sort of the attempts are made, then a mission status result is reported back to, say, the experimental frame. And so the components in these models, the one of interest is the interceptor. This is shown in a Markov state diagram. There's the state decide that can stochastically transition to either hit or miss based on a probability of our choosing. So in principle, the basic way of studying this would be a Monte Carlo sampling simulation, but we'll show that ParaDEVS is a faster way of getting the results. So yeah, here's just a demonstration of a single Monte Carlo sample. This was running for 100 threats, and the shoot, look, shoot strategy, and it gives us results for one sample. So in principle, we would run that n number of times, and we'd get statistics for the simulation. The other component is ParaDEVS. So this is kind of just going to break down some of the steps that we take to generate a ParaDEVS solution, but there's a make general tree function. The advanced leaf front is the thing that creates branches for each possible choice in the simulation. And then the equivalence is done so that the growth of the tree is reduced from an exponential growth to something more manageable, like polynomial, linear, depending on the system. And then there's some implementation details shown in the global state transition and so forth. So at the top level, we're going to be simulating 4 simulations in parallel. 2 of them are going to be running ParaDEVS, and each one's going to be doing a different strategy. So one's going to be a ParaDEVS simulation of the single shot, and one's going to be the ParaDEVS simulation of a shoot, look, shoot strategy. And then equivalently, we're going to have 2 Monte Carlo sampling simulations going on for the same 2 strategies. In this case, we're doing 1,000 simulations or 1,000 samples. But you would increase that for better accuracy or decrease. So altogether, I have this script that will start up in separate sub-processes. First, the coordinator that sets up the root coordinator system by running the run control. And then I start up sub-processes for each of the components in the model. So there's an experimental frame, there's two tree atomic models doing ParaDEVS, and then there's two Monte Carlo simulations going on as well. So when I simulate this, there's going to be a little bit of startup time, but there's going to pop up on my screen a graph where it's the number of hits on the horizontal axis versus the probability on the vertical axis. So it's a distribution of the hits. And it'll start out blank, but as the results come in, they will be plotted directly on the graph. So what we expect to see is ParaDEVS solutions come in first, and then after some time, the Monte Carlo sampling solutions come in later. So some startup time, and here's the graph. So the simulations are currently running in parallel right now. And then there we go. We have a red and blue graph for ParaDEVS single shot and shoot look shoot results. And it'll take some time for the Monte Carlo results to come in, but the benefit of these ParaDEVS solutions is that they're in principle have total knowledge of this system because it's a simplified system. Oh, there come the Monte Carlo results. So yeah, the ParaDEVS results have data for these super low probability events like low number of hits, some things that would very unlikely to happen. Whereas the Monte Carlo results, now that those came in, we see that they generally match up while taking longer, but there is some sampling error in the results. So there's some difference between what we theoretically expect that we get from ParaDEVS and the true solution. So yeah, this essentially the Markov or Monte Carlo simulations not only took longer to gather data for, there's also an error associated with them. So this was 1,000 samples. So the error goes like square root of n, roughly. So if you wanted to increase the accuracy of this result, that would sort of go up as n squared, number of samples squared. Whereas ParaDEVS would be constant in this case. So that about covers it. So thank you for your attention.